All right, so I'm Avery Regier. I work with John Deere. I've been developing and supporting web applications and services for the last 2 decades. And so a lot of this comes out of what I've learned, especially in the last 3 or 4 years as we've been supporting a particular service as well. No one ever does anything alone. So these are a lot of the people that contributed and encouraged and helped throughout this process of building what I'm showing you here today. So let's foretell. What are we going to talk about today? So I'm going to start with my motivations. Why did we build what we built? What kind of a problem did we have? And why are we doing this? And we're going to talk about observability, making sure that your systems are you're able to see what's going on inside your systems. Then we're going to go and talk through these 3 different forms of failures that I was observing inside my systems after I had that observability in place, and we recognized that was things that were killing us regularly. So we're going to talk about zombies, black holes, and tribbles. How to recognize those things coming and handle them or avoid them. All right, so my motivation. So we had a large Java-based monolithic API. Now you may debate, should we have that API or not, right? Should it be a monolith? Should it be a microservice? Reality was, this thing is a monolith. And there are a lot of great reasons why it couldn't get broken down, or at least not yet. There's 50-some dependencies that this thing has. It does a lot of different things, 400-some APIs in it. And so, if one of these dependencies has a problem, often the whole thing would go down and affect everybody. So essentially what you've got is cascading failure. This thing was often a victim of things that were going on downstream. So how do you get a hold of this situation? How do you try and get it to the point where this thing can handle those problems going on downstream? So, you can try and resolve, try and find all your root causes, all you want, okay? But it's like playing whack-a-mole, right? Because, say you solve this one deadlock situation in some downstream system that has a database and has a table, but right next to it there's another table, and that other table's got some different characteristics, and maybe it's the one that deadlocks next, right? So it's like playing whack-a-mole. What we really want to do in these cases is try and suss out and figure out what are our failure themes. Why do things go wrong? How do they go wrong? And are there warning signs that we can use to detect how we're getting into that situation, and can we do something to try and get ourselves out of that situation, all right? So some of the failure themes that we had were resource exhaustion. You've got only a certain number of database connections because that's how much your database can handle, right? And sometimes stuff happens and you use them all up. Maybe some of those reasons for that is long-running work, just something that someone started off and it took 4 hours and it was loading in gobs and gobs of data. Maybe you were getting slammed by incoming connections from your clients in an unusual way. Someone just built a new feature and suddenly you're getting it out there, but they didn't even know they were going to slam you like that when they put it in production. It might be the cascading failure. You've got a downstream system that has a failure, and it's now starting to affect you. So these are warning signs. We can use them. There are warning signs, sorry. You can use them. So the first thing you need in your app is observability. And this observability comes in 2 different ways. One, it's for your code. So if you have observability where your code can observe what is going on in the other parts of your system, now you have the information you need to start implementing automated resiliency, and that's what the whole rest of this talk is really about, okay? The other thing you want observability for is, for you. You want to get the information about what your application is doing and get that into some kind of centralized logging. Use lots of great metadata that can drive your dashboards and alerting. Now, this is what is really being talked about next door. And I really encourage you all to go and afterwards go out and get the video for that because it's really important concepts and that will help you here as well. So the foundation for all the things that we're talking about is work tracking within the application itself. So what is a good work tracker? A work tracker is something that is not going to block your real work. It's something that you can put inside your code, and it's keeping track of what's going on at that moment. What are all the parallel processes that are going on at the moment, and what does it look like? So if you're going to be doing something like that, my number one concern when I went to do this was, I want this thing to be safe. I don't want this thing to, in any way, if I had this thing in, be the cause of another outage. I've done that enough in my life. I don't want to do any more. So I was being very, very careful about that. You know, one of the great places where those outages come is because you've got deadlocks and things like that. So a good work tracker will be non-blocking. It should order by the oldest thing first. So whatever you first put in there, it stays as the first thing, and eventually, as the old things go out, your currently oldest thing is the oldest thing there, because it turns out that oldest thing is the thing you most care about, and it's most likely to be the thing that's going to cause you a problem. You need to be really cheap to delete. So if you've got 1,000 things going on in your system, you don't want to be constantly, every time something completes, or you've got a lot of small little bits of work, you don't want it to be searching through the entire list and then and having to remove it, or doing a copy on write would be terrible in this case, right? Because you're constantly writing and removing stuff from this list. It also needs to be able to clean up after itself, make sure it's not creating garbage situations, whatever else. So real quick hint, we were a Java-based system. Such a thing, beast as this, does not exist in the JDK. You can try and look for it all you want amongst the concurrency things that are there, but it's not there, and it doesn't really exist in any other open source projects that I know of. I looked really hard. So if you're probably going to end up having to build something like this, if you do, you want a good API design around this. So the idea here that I landed on was the idea of you take a ticket, from this work tracker, and you're giving it the payload, and it's going to keep track of that payload. And then when you're done with that work, you're just going to return the ticket. The ticket knows wherever that thing is stored, and it can delete it really cheaply. And then you should be able to stream all your existing payloads or tickets out through that by age. And then you can do all kinds of fun things with it. So watch this space. I am working on getting this open sourced, so you don't have to go write it yourself. It was an effort. But watch that space. I was hoping to be able to actually announce it, and it's here, and you can go look at it and try it out. But hopefully within a month or two, we will have it out there for you. This would be how you use a work tracker real quick. So maybe you've got this, so we have this, our work tracker, I called it outstanding. So there's a number of outstanding things you're keeping track of. T's the ticket or the thing that your payload that you're keeping track of. And then it has a ticket that it'll return to you. And that when you're done, it'll use the autocloser. So somewhere inside your application, at the very highest levels, if you're a servlet-based API, you would typically use a filter. And so the servlet request that represents your work that's incoming. It has all the information about what is going on with this request. So you can go and get a ticket, create a ticket out of your work tracker. You want to somehow collect this information about what it is, put it into some small little bean that is just keeping track of the basic information that you need, and maybe a reference to your threads, and then go do your filter. In other words, go do all the work, right? And when it comes back around, this is a try with resources, so you know that that ticket that is currently ignored there actually gets closed under the covers when you're all done. So the really important thing there now is you want to make sure that you're tracking the information that you need in order to make the decisions later on to help you figure out, am I in a bad situation? So here I'm mapping that work identity. I'm looking at things like, say, the remote address. Okay, where's this traffic coming from? The path, what kind of service is it calling? Is it calling my get foo versus my get bar? Maybe the remote users. So this would be who is calling this. They could, one user could be using a lot of different clients and coming from a lot of different places, but maybe it's just this one thing that got a hold of the ability to call your app that might be hurting you or something like that. I'll track all your work by session ID. Just whatever you can find in whatever system you've got. Spring gives you a lot more options as well, and it depends on what kind of authentication you're using. Maybe you're OAuth, and so you've got client IDs and things like that you want to track. So basically, whatever you can find out that is going to summarize the kinds of work that is coming to you. In your bean, you also need a few other things, like when did you start? You basically keep track of the time. Keep track of the thread or whatever that is actively doing this work, and assign a request ID. You stick that into the MDC. When you go and do your logs, all your logs then are going to tie up to this one thing, and you're going to be able to see everything that's going on with this particular thread. All right. So now we start talking about the different kinds of failures that we were seeing. So the first one is zombies. So zombies are the undead. They're long-running but abandoned requests. They eat brains, i.e. your system memory. They cause havoc, i.e. crash the system. And long after its progenitor, or maybe the guy who started that work, and he thought it was dead long ago, but so he gave up and he probably made more, hit refresh. And he tried again, and this creates a zombie horde. So how do you know that you have a zombie? For us, first off, we just looked at when do we know that our clients are no longer interested in whatever this is. So for us, we had web servers in front of all of our JVMs, in front of our servers, that by default had a 5-minute timeout. So I pretty much know that except for specialized things like files uploads and downloads and stuff like that, I know for sure that if it's gone beyond 5 minutes, this is work that I don't care about anymore, and the only thing it is a danger to my app. So I'm going to try and detect this, but some things. Perfection is not required. It doesn't have to be perfect. You just want to get this bit of work before it starts causing instability in your app. How could these things cause instability? Well, for instance, maybe it's just loading a bunch of data via I/O from some back-end system, and it's taking the whole lifetime of all the information you have about this thing, and it's loading it all up inside a collection inside your JVM. Eventually, what's going to happen? Out of memory, right? Depending on how much stuff you've got out there. But if you've got a really big heap, like Java supports these days, this could take hours. And slowly your service is just grinding to a halt. The key thing is that we want to get it before a human would, and often this is much, much faster than a human ever would. And often the human wouldn't even get it until the system is actually crashed, right? So we want to keep these things visible. We want to somehow log the long-running work using some kind of a background thread. We can use our work tracker, and every 30 seconds, log the things that have taken more than 30 seconds. That seems to work pretty well for us. So in those moments where you're not quite sure if the undead are really dead, don't get all stingy with your bullets. All right, so how do you kill a zombie? Often, there's usually 3 types of zombies that you might want to deal with. They might be waiting on stuck IO. In this case, just using interrupt often works decently well. It's not perfect. It'll throw an interrupted exception. Sometimes things catch that, and it will keep trying, but often enough, it does work, so give it a try. It could be that this thing is just constantly making lots of different calls to other backends, and so the interrupt, it's not stuck on I/O at that point, and so it'll keep trying, right? And it's hitting other things. In this case, if you use some kind of a generic proxy in your code, that every time you're making a backend call, it goes and checks to see whether or not you've run out of time, then this thing can just throw an error. So we'll see what that looks like. First off, this do work. This is our logging and killing stream. So first off, we're going to filter and just find out, is this thing loggable? If it's loggable, if it's hit more than 30 seconds, then we're going to peek at it and go ahead and log it. When I log it, I want to make sure to get any metadata that I know about that zombie. So it's looking at that work object that we created earlier and logging all of that information. That way I can know actually what this thing is, who conjured it, who made it. I need to tell that information to myself. Then filter down to just the ones that are older than, say, 5 minutes or whatever your threshold happens to be. And then those are the ones I want to go kill. Nice and simple process. This kill runaway down here is something that you would call from your REST template or something like that. Every time you go out to make another REST call, just before you make that call, go get the current work that's outstanding and find out if it's a zombie. If so, shoot it in the brains. Throw an error. Make sure it's an error, not an exception, because typically the exceptions will get caught or something, and then it'll retry and you haven't succeeded. But throw an error, and hopefully that should resolve that situation. Later on, you'll want to be able to catch that error, transform it into something that tells the client, this was a bad request or something like that. All right, so last form of zombies is this really long-running single back-end call, where maybe it's a deadlock situation or something. Well, here prevention is key. You want to be able to see those requests coming. You may not be able to kill all of these, but you want to be able to know the situation is ongoing for some things and be able to kill them. So for this, we need to discover black holes. So black holes are these dependent services that take connections, but they never give them up. They just eat and eat and eat. Or maybe they just perform so poorly for a time that it just takes all your server's attention away. Like, trying to skirt the edge of the event horizon of your black hole. You lose a lot of time, right? A few centuries later, you might get past. But eventually what happens is all of your server's attention, all of your threads get focused in on this one place. So eventually it just takes them all up, and there's no room left for anything else. It looks like this. Say I've got a very simple system that only has four threads or resources or something available. And I've got blue work that takes a little bit longer, and I've got the orange work that goes real quick. Okay, this is how this looks. And so suddenly the blue work starts taking just a little bit longer and a little bit longer. And notice as I'm taking up more and more time, I've got the same amount of work, but it's now taking up more and more of my resources. And it takes a little bit longer, and boom. Now all of a sudden, I've taken up all my resources, and now I'm rejecting work, or I'm failing work, or maybe even worse, it's queuing it up. So, and now it's affecting not just the blue work, it's also affecting the orange work, right? The stuff that is quick and good, and you want more of that stuff, right? Because it's quick and good, and you can take care of it. Not this blue work. So how do we deal with this? So we're going to start with an analogy, and you've probably, anyone has seen Hystrix, Netflix Hystrix, they use this kind of analogy. There's a number of other open source tools that do this too, but they're not necessarily geared towards dealing with black holes. So this analogy, so a circuit breaker, it is meant to detect an overload of electricity in your system. It opens up or breaks to protect your appliances, prevent fires, etc., whatever else from going on. I'm not going to talk too much about the terminology. We'll just let that go, and we'll just say it's broken. Okay, so this can be, switched back, typically manually when the event is over. So what's the main problem with circuit breakers? I need some help here. You have to manually reset them, right? So the circuit breaker trips because maybe there was a lightning strike somewhere. It was a very quick event, but your whole house is dark. You're now trudging down through the bottom of your basement, trying to find the circuit, find the circuit breaker, find a flashlight, trying to, and turn it back on. That's a whole lot of time, and maybe you weren't even home, right? Maybe you're off on a trip, you're at a conference, and you come home and suddenly everything in your fridge is bad, right? Because you didn't have the ability to get there and go and just turn it back on, because that's all it was really required. So that is definitely the main problem. We don't want a circuit breaker that's just going to stay broken. So what are our goals in trying to prevent and find this kind of situation? So first off, I want to make sure that there's no human intervention necessary at all. I want this circuit breaker to dynamically understand what normal is and then detect when things aren't normal. I want it to prevent sending more requests into that non-normal situation. Fast fail them. Those requests are going to fail anyways. Just tell the user, hey, this thing's broken right now. You can't do it. I want it to then detect when things are normal again and then heal the system automatically, because this may be a very short duration event. I don't want it to create a long outage for my application. And with that in mind, I have this other idea or goal, which is that we want to protect our service over protecting the traffic. We do have this goal. We want to do kind of fast failure for our clients. But sometimes, what if you could take that call and do a test, see if one of those works? And if one of those works, then I know that my black hole situation has passed, and I can automatically reheal. The other thing, and I'm not going to go into too much detail on this, is that human intervention is possible. I want to be able to basically lock this in a particular state or tell it to go retest or something like that. I also don't want it to limit the scalability or impact my users in normal situations. There are a lot of things. Hystrix uses pooling, for instance. But the problem with pools is that, again, they limit your scalability. It's yet another resource, actually, that you have to protect. So here's our plan. First off, we want to figure out how do we understand what normal is. Second, we're going to look at just how messy this can get. We're going to talk about how do we intervene in this situation, and then we'll have a demonstration at one point. So let's look at the basics of your circuit breaker. How do you do this? Well, first off, you want to use that same kind of work tracking analogy, but now you're going to use it on your dependent services. So every time you go in and you're going to hit that dependent service, you're tracking the work for that dependent service only. We're going to find, based on that work tracker, when stuff comes out of that dependent service, we've now got an elapsed time because that was part of our work tracker, right? We can take all these elapsed times, find the standard deviation. What is the norm for that particular time? We can also find the mean. What's the average of that? And then typically, if you've got a relatively normal distribution on this, which is not always the case. Sometimes it looks very non-normal, but close enough, and close enough is usually good enough in this case, that you can take the mean plus 5 times the standard deviation, and this roughly equates to almost all of your hits against this back-end service. So all of them should finish within that time frame. That's your threshold. That threshold is really important. So if the average of the things that you currently have in progress, because you've got a work tracker, you can go through the work tracker and see what are all the things that are currently hitting this back end. We're going to get the elapsed times that they have done so far. Take the average of those, compare it against our threshold before we actually make a new hit. And if it has above that threshold, then we're going to say, boom, I'm going to break. I'm going to send myself into just a testing mode on this. I'm not going to let anything through until they're all done. And then I might send one at a time after this to go and test. So this is what taking those statistics looks like. So we have in the dark blue, we have our mean that gets a little bit better over time as we start taking statistics. Down here at the bottom, this is not really time. This is the number of hits that we've had against this particular dependency. One of the things that we're doing is after 50 hits, we're now starting to trust our statistics, so I've generated a threshold. That's what the dotted red line is. Notice that that dotted red line is just short of what our max is that was discovered as we were going through this. So most of our hits are all 99.5% are all hitting within that threshold. The other blue is taking the standard deviation and plus or minus off the mean. So you can see that in general, what I'm currently seeing as my mean in the last set of hits that I discovered, that's the black line, and it's staying generally within that threshold. All right, so now it's time to demo this and show you that it actually works. All right, so right here we have an unprotected client. I'm going to show you what happens first when you don't have this protection in place. So I've got a client over here, and in the middle I have my server. And this blue line represents kind of the number of hits that I have currently going on against my server. All right. And down here is just some things about that dependency and what's going to happen with that dependency. Now I'm going to send that dependency into a black hole. All right. At this point, we have some kind of deadlock situation or something like that. It's not responding. It's taking the hits, but it's not responding. So you can see that your threads, whatever you've got available in your system, it's filling up. If you've got WebSphere, I'm sorry, but currently you're queuing up all of those hits, and you are going to handle those eventually, even if no one cares about them anymore, but you are going to handle them. And say eventually you get rid of the black hole situation, and now you've got to get through the queue, work through all that stuff. Maybe you happen to recover. Usually you don't, honestly. If you've gotten into this kind of situation, chances are you've got to bounce the thing. All right, so here's our protected situation. I've got a circuit breaker that is protecting it. So we're going to give some traffic here. And we're now going through a relatively normal day in the life of this particular dependency. While this is happening, I'm keeping track of how long this request took in the background. And eventually I get enough data, I set a threshold, and now I'm going to go into a black hole. Boom. So that quick, it was able to detect that I was going into an unusual situation, open up the circuit, and put myself into a half-open situation. The half-open basically means that if I've got any requests going against it, I won't let any more requests go through. If I have no requests going against it, I'll let one through to test it. So let's say our infrastructure guys have eventually gotten word of this. We go fix the black hole situation. We fix whatever's going on in the database. It's going to have to drain a little bit. Now we're in that open situation. And then, so we tested. We found out that things were normal again, and the system went back to normal, and it survived. I didn't have to bounce anything. I left a whole bunch of headroom up there for other things to get work done that don't depend on this dependency. Let's see. All right. So, but it does get messy. So we need to use some heuristics as we're going and looking through this information. So first off, there could be, say, poison messages that aren't representative of the normal situation, and they just cause really long-running work. And so sometimes they can cause your circuit to break. So one heuristic that we use is we don't consider that oldest thread when calculating our average. We just let that guy go through. Okay, we use the next ones. If there's enough of that poison work, yes, it could cause a problem, but usually there's only one. Low usage services, and I have just ran out of time, yay. So there could be low usage services, so you might want to just wait for a certain number to build up before you start calculating, or you might just let your zombie detector deal with it. Some things are just naturally slower, and like lists versus single items, we might want to weight things and say that my list is getting a far bigger weight than my just going and getting one thing out of the dependent service, and so we can divide that weight, the elapsed time by the weight, and we can kind of get a better elapsed time per item that I'm going to fetch from the service, or you just create a lot of different small little circuit breakers. We're going to completely ignore exceptions because they don't tell us anything about establishing a threshold. They don't tell us anything about the health of the service. But what if there is a flood of calls? So very quickly, for that, we need to prevent tribbles. So tribbles, they are similar requests that you would normally invite, but they just come too many too fast for your service to handle. And as they take your attention, and then they eat up all your resources. So how do you get tribbles? It might be a friendly, unintentional denial of service attack. So it might be something like an innocent parallelism. So you return maybe a really long list of results, and the client then turns around and asks for details on every one of those results from your service. And then they do it in parallel. You know, maybe there's 1,700 requests. We actually had that situation. And so we just got flooded with 1,700 requests all at once. And you know, that used up all of our database connections, and we could do nothing else. Could be overwhelming retries. It might be a situation that just looks like a Tribble. So it might be your own failure to scale and meet the normal demands, but you do still need to protect your service and allow things to go through. It might be cost allocation failure. Maybe you just haven't provided any incentive for your clients to limit their usage. It costs nothing to them, so they're going to abuse you. Might be architectural misuse, where you just haven't provided the right services for the clients to use for the kind of thing that they want to do. How do they hurt you? Well, they can maybe take up all your database connections or threads or some other resource. And often when writing the limit deadlocks result. So if you've got 15 available connections, you're using all 15, sometimes that work needs another connection to finish. And so you end up with these deadlock situations where I'm full up of all my threads, I'm full up of all my database connections, and all the threads that need another database connection, they can't get it because of the slam of work. Sometimes you overwhelm your downstream dependencies. Sometimes you just queue up, leading to retries. All right, so Captain Kirk, when he got a bunch of tribbles on his ship, what did he want to know? He wanted to find the guy who sent him the tribbles, right? He wanted to find Cyrano Jones. And he also wanted to stop them coming in, right? So he wanted to say, close that door. In the trouble with tribbles, Klingons were kind of a Klingon tribble detector, or actually the tribbles were a Klingon detector because they hated each other. So we needed some way to detect these things. First off, so we're going to, again, use our work tracker. We want to enforce an overall limit of the number of things that we can do at once. So if we've already used up 90% of our resources, just start rejecting all work. But we hopefully don't get there, because first we want to detect similarities in our incoming traffic. Is it just one particular user who's causing this problem? Is it one particular kind of client, one of your business partners that's causing this problem? Maybe it's a particular downstream API that's having a problem, that has a deadlock, but it's not affecting the other ones that you're using. Using your work tracker and using the information you kept track of, you can basically go through the work and filter out down to just the ones that meet that criteria, that are the same as this thing that's coming in. And if there's too many of that same thing that are coming in, then you just reject the work. You've got to be careful as you're making that decision, though. Don't use up any of your resources that you want to protect before you make that decision. So you need to use header information, maybe in-memory cache data. You want to avoid database access unless you're feeding the cache. So then we need to evict them. We want to allow spikes, but we want to give headroom for normal traffic. So basically, short story is use a status code 429, too many requests, which is often used for rate limiting schemes. This one is not really a rate limiting scheme. It's really a, you're doing too much scheme. It really does mean too much traffic in this case. But you can really be friendly with them because you have a work tracker. So you can tell it how long, say, your oldest bit of work that meets this criteria is taking, and you could tell them, come back after that amount of time. That's often much shorter than, say, them having to just error out. They could actually give a reasonable retry. Sometimes those retries are going to be either too short and too quick if you don't tell them, or it's going to be way too long, and they're waiting unnecessarily, right? So you can be really friendly. Tell them how much time to wait because you actually know that information. So Scotty says, I gave them to the Klingons, sir. Klingons? Aye, sir. Before they went into warp, I transported the whole kit and caboodle into their engine room, where there'll be no trouble at all. All right, so we don't really have necessarily time for questions because we need to be kind to the next guy. But there's a bunch of things that I did not talk about here. You can kind of see that in the list. I would love to talk to you. I want to create a conversation around this. The reason for me doing this presentation at all is because I want to know what you know that I don't know. And I want to help us improve together in how do we provide reliability in our systems. Maybe this doesn't apply to you. That's okay. I still want to talk to you. All right? So that's it.